Welcome to the Deep Dive. We cut through the noise, get straight to the insights, the stuff you really need to be well informed.
Glad to be here.
So today, we're plunging into something that's, well, it's everywhere. AI progress. It seems incredibly fast, right? You see these benchmarks, the scores climbing.
They are? Constantly.
But what is that performance, hitting 90% on some test? What does it really mean? Like, in terms of what AI can actually do compared to a person and how it impacts the real world?
That's the million-dollar question, isn't it? Because those traditional benchmarks, they often give you a snapshot, maybe of test-taking ability,
Right.
but not the whole picture, not its practical use out there in the wild.
Okay, so for listeners who are used to hearing AI aced GLUE or killed it on Super GLUE, what's a fundamental problem with those old ways of measuring? Why do we need something new?
Well, the study we're digging into today from MTR makes a pretty clear case. They argue those benchmarks often fall short. For one, they can be quite artificial, sometimes even adversarially selected, meaning they're designed specifically to be hard for the current models.
So it kind of biases the comparison to humans from the start.
It can, yeah. And maybe more importantly, they saturate really quickly. A model gets good at a benchmark, and suddenly it's hard to see real progress anymore.
Okay.
You can't easily compare, say, GPT-2 from 2019 with a brand new model like O1 using the same saturated test. So we've been left sort of estimating difficulty qualitatively, guessing, really.
Right, squinting at charts, trying to figure out if a model's generally smarter or just better at that one specific game. Sounds like we needed a better yardstick.
Exactly. We needed to move from these abstract scores to something more tangible, more grounded.
Which brings us to the core of today's deep dive. This new metric from Model Evaluation and Threat Research, METR. What is it?
So they're proposing something called the 50% task completion time horizon.
Okay, break that down.
The core idea is actually pretty intuitive. It's the typical amount of time, the duration. It takes a human expert, someone with relevant skills,
Right.
to complete tasks that a specific AI model can manage successfully 50% of the time.
I see. So you're directly comparing AI success to the time it takes a skilled human.
Precisely. It grounds AI capability in human experience in time, which we all understand. We're looking at a recent paper by Thomas SWAA and colleagues at METR that outlines all this.
And our mission today is basically to give you the shortcut, the key insights from that research.
That's the plan.
So grounding it in time makes sense, but how did they actually measure this? What kinds of tasks are we talking about? It must have been quite an undertaking.
Oh, it was. They put together this incredibly diverse suite, 170 tasks in total.
170.
Wow. And designed specifically to capture skills you'd need for, say, research or software engineering roles. It wasn't just a few puzzles.
Okay, give us some examples. What did these tasks look like?
Okay. So first, they used a set called HCAST. That's Human Calibrated Autonomy Software Tasks.
Okay.
97 different software tasks in there. And they ranged hugely in difficulty. Some were like 1 minute long, look up a fact on Wikipedia, that kind of thing.
Simple enough.
But others went up to 30 hours for a human expert. Things like fixing really subtle bugs in PyTorch code or writing complex CUDA kernels.
30 hours. That's a serious piece of work, not just a quick coding challenge.
Definitely not. These are realistic tasks you solve using, a standard bash shell, text editors, the usual tools.
Okay, so that covers a wide range of software tasks. What else?
Then there was SWE-bench. 7 challenging tasks specifically focused on ML research engineering. Each one was designed to take a human expert about 8 hours.
Right, so more complex, specialized stuff.
Exactly. And then, crucially, they needed to measure the really short things, too. Because AI models have been decent at quick stuff for a while, right?
Well, that's a good point. How do they capture those quick actions?
That's where the third set, SWAA, comes in, Software Atomic Actions. This was a new set they developed. 66 novel, shorter tasks, mostly single-step things, taking maybe 1 to 30 seconds for a human.
Like what?
Things like identifying the language of a code snippet, doing basic math, simple code completion, maybe triaging an alert. Those common quick actions you do all the time as a developer.
Gotcha. The little building blocks.
Exactly. And this SWAA set filled a really important gap for measuring the capabilities of older models and also just getting fine-grained data on those very short tasks. The key across all these tasks, though, is they're designed to isolate a specific unit of work. Usually less context needed than, say, a whole multi-day project.
That makes a lot of sense. Isolate the capability you want to measure. So they have this huge, diverse task suite. How did they get the human time baseline? Who did these tasks?
Right, the human baselining. This was also extensive. They got skilled professionals, people with, on average, about 5 years of relevant experience, many from top universities.
So actual experts.
Yes. And these experts were timed doing these tasks. They collected over 800 individual baselines, which added up to more than 2,500 hours of recorded human effort. That gives you the ground truth, the human time, to compare the AI against.
That's some serious calibration. Okay, so we have the human baseline. How did the AIs do? Which models did they test?
They looked at 13 frontier models, spanning releases from 2019 up to early 2025.
So a good range showing the progression.
Definitely. And they ran these models using what they call agent scaffolds. Think frameworks like React, where the AI interleaves reasoning steps with taking actions, like running code or editing files.
Right, making them act more like an agent trying to solve the task and the results.
Pretty stark contrast over time. The earlier models like GPT-2, even GPT-3, they really struggled once tasks took longer than about a minute.
Right.
But the recent frontier models, things like Claude 3.5 Sonnet or the O1 model, they're successfully tackling tasks that took those human baseliners over 4 hours to complete.
4 hours of expert human work. Now within reach for these top models. That's a big jump.
It really is.
And this is where it gets really interesting, right? Looking at the trend over time using this new time horizon metric, what did they find?
This is the headline finding, really. And it's quite astonishing. The study found that this 50% task completion time horizon for the best AI models, it's been doubling roughly every 7 months since 2019.
Doubling every 7 months. Let that sink in. So a task that takes an expert, say, an hour today, AI might handle that with 50% success in just 30 minutes worth of human equivalent time 7 months from now.
That's the trend they observed, yeah. About 212 days for that doubling at the 50% success rate.
That pace is just staggering. What's the biggest implication of that speed for people listening, maybe working in tech or research?
It means the goalposts for what AI can potentially automate or significantly assist with are moving incredibly fast, faster than many probably realize. Now, they also looked at an 80% success rate.
So more reliable performance. How did that look?
The doubling time was actually very similar, 213 days, still around 7 months, but, and this is important, the actual time horizon length for 80% success is much shorter, about 5 times shorter.
Meaning?
Well, take Claude 3.7 Sonnet. Its 50% horizon was around 59 minutes in their measurement, but its 80% horizon was only about 15 minutes.
Okay, so getting AI to be reliably successful on longer, more complex tasks is still a much bigger hurdle, even with the rapid progress overall.
Exactly. Reliability on complexity is still the challenge.
So just to anchor us, as of early 2025, these frontier models are hitting that 50% success rate on tasks that take experts around 50 minutes. That's already quite substantial. What's driving this crazy acceleration? Is it just bigger models, more data, or something else going on?
The study suggests it's more nuanced than just scale. They point primarily to the AI's improved reliability, its ability to adapt when things go wrong, combined with just better logical reasoning and, crucially, better tool use.
Okay. So qualitative improvements, not just quantitative ones.
It seems so. It points towards the kind of maturation of these AI agents beyond just raw power.
That's a really key distinction. It's not just throwing more compute at it. It's that the models are getting fundamentally better at the process of solving problems. Let's dig into that qualitative side. Yeah. What are they really excelling at now compared to, say, a couple of years ago?
One of the biggest shifts they highlight is robustness to mistakes.
How so?
Well, historically, older models would often get stuck. They'd try something, it would fail, and they'd just repeat the same failed action over and over, an endless loop.
Right. Frustratingly dumb.
Exactly. But the current models show a markedly better ability to course correct. They give an example. With GPT-4, over a third of its failures on their tasks came from repeating failed actions. But with O1, a newer model, only 2 out of 32 failures were due to that.
That's a huge difference.
It is. They can pivot now. If one approach fails, they might try something completely different, even rewrite entire files. That's a big leap in practical problem solving.
That ability to learn from error, or at least change tack, feels much more intelligent. Does that come from architecture or training or both?
Yeah.
And how does it link to using tools better?
It's likely both: better training, focusing more on sequential decision-making and error recovery, and perhaps architectural tweaks too. And it absolutely links to tool use.
Okay.
Early models like GPT-3 struggled even with basic syntax for calling external tools or APIs. Just getting the command right was hard.
Yeah, I remember those days. Lots of formatting errors.
Right. Now, the frontier models, they can generally use tools pretty effectively. They can edit files efficiently instead of using clumsy line-by-line commands. This means they interact with code bases or systems much more naturally. And crucially, if a tool use attempt fails, they're better at figuring out why and trying again correctly.
Makes sense. And what about basic logical reasoning and code generation? We hear about benchmark improvements there all the time. Does this study confirm that translates to these practical tasks?
Yes, it does. It's consistent. Models are simply better at writing code that's syntactically correct and also semantically correct code that does what it's supposed to do.
Yeah.
They're also better at interpreting complex instructions.
On an example.
Yeah, they mention one where an older model might see tallest building in the world in 1972. It might misunderstand that as the tallest building that was built in 1972.
Ah, a subtle but important difference.
Right. Whereas a newer model correctly gets the common sense meaning, which building existed and was the tallest in the year 1972 whenever it was built. That shows better handling of nuance, context, and, well, common sense.
That's definitely progress.
Yeah.
But they can't be perfect yet. Where are they still falling short? What are the current weak spots?
Oh, definitely not perfect. A major area of struggle is dealing with a lack of clear feedback.
What do you mean by that?
AI agents still do significantly worse when there isn't an easy way to tell if they're making progress. Like if there aren't unit tests they can run or clear error messages, tasks where finding out if you're right is costly or slow. They use the term black box functions. Those are particularly hard.
Yeah, I can relate to that as a human. Trying to debug something where you just can't see what's going on inside,
Yeah.
it's maddening. So AI struggles there too.
Very much so. If they can't quickly verify their approach, they can get lost. Another related challenge is proactive information seeking.
Proactive seeking.
Yeah, models tend to just assume they know how to do the task. They jump in and only rethink things after they hit an error. They often don't pause first to gather relevant information.
So they don't read the manual first.
Pretty much. Like if they need to use an API, they might just guess or hallucinate some API endpoints.
Never there.
And only after getting slapped with errors do they maybe go look at the actual documentation. Or another example, needing a file's encoding type. Instead of running a simple file command to find out, they might just inefficiently try decoding it with UTF-8, then Latin 1, then something else, trial and error instead of finding the answer directly.
That sounds computationally expensive and kind of inefficient. Almost like a lack of basic curiosity or planning.
It points to a limitation in their strategic thinking, perhaps. So overall, the study finds that AI agents perform worse on tasks that are qualitatively messier.
Messier.
Yeah, meaning tasks that lack those clear feedback loops or involve dynamic, changing environments, or ones that really require that proactive information gathering we just talked about. It contrasts with their improved structured reasoning on cleaner problems.
Okay, that paints a clearer picture of the current state. But this always brings up the big question. External validity. Do these findings, this doubling trend, actually generalize? Or is this just performance on a specific set of lab tasks?
A crucial question. And the researchers did try to tackle it. They actually rated all their tasks based on 16 different messiness factors.
Like what kind of factors?
Things like, is the task resource limited? Does it involve novel situations the AI hasn't seen? Does it require real-time coordination? Does it have unclear feedback? That sort of thing.
And what did they find when they correlated messiness with performance?
Well, first, as you'd expect, AI agents do perform worse on messier tasks. On average, an increase of 1 point on their messiness scale reduced the success rate by about 8%.
Okay, so messiness makes it harder. No surprise there.
Right. But here's the really interesting part. The rate of improvement over time, that doubling trend, was similar for both the less messy tasks and the more messy tasks.
Oh, so they're getting better at the messy stuff at roughly the same exponential rate.
That's what the data suggests so far. There wasn't evidence of a plateau specifically for the harder, messier tasks. That implies the trend might be more robust than we'd initially guess.
That's actually quite significant. Did they check this against other benchmarks too, like established ones?
They did. They applied the same time horizon methodology to SWE-bench Verified. That's a pretty standard benchmark now, using tasks derived from real issues in open source software repositories.
Did the trend hold?
Yes, it showed an exponential trend there too. But interestingly, the doubling time was even shorter, around 70 days.
70 days. Whoa. That's incredibly fast, almost too fast. Is there a catch?
There is a potential caveat, yes. You're right to be a bit skeptical.
Okay, what is it?
The faster trend on SWE-bench might be partly an artifact of how its human times were estimated. Those times are often based on how long it took the maintainers of the repositories, people with deep existing context about the code, to fix the original issue.
Ah, okay, so the human baseline is super expert high context time.
Exactly, which likely underestimates how long it would take a less familiar, lower context human to tackle the same problem, especially the easier tasks.
Right, so if the human baseline time is artificially low for easier tasks, it makes the less capable older AI models look comparatively worse.
Which then makes the progress curve look steeper when the newer models start solving those tasks. It could inflate the perceived rate of progress compared to a more general human baseline.
That makes perfect sense. So SW-bench confirms the exponential trend, but the exact speed might be debated due to the baseline issue. What about testing on completely real, uncontaminated work? Did they try that?
Yes, they did something pretty cool. They ran some frontier models on actual internal pull requests from METier's own software repositories. Stuff the models definitely hadn't seen in training.
Okay, now we're talking real-world application. What happened?
It yielded some fascinating comparisons. First, they found that human contractors brought in to fix these internal issues took, on average, 5 to 18 times longer than the internal METR maintainers who already knew the code base inside out.
Wow, that context difference is huge. 5 to 18 times longer.
Massive difference. And here's the key part. The AI agent's performance, its success rate on these real-world PRs, was consistent with the success rates you'd predict based on the contractor's time to complete, not the maintainer's time.
Okay, that is really interesting. So the AI's capability, measured by this time horizon, it seems to map better to a competent but low-context human worker rather than the deeply embedded expert.
That seems to be the implication, yes. Which makes sense, right? The AI doesn't have years of experience with that specific proprietary code base. It's coming in relatively fresh, like a contractor would.
Yeah, that tracks. So maybe AI right now is more like a very capable, fast junior developer or a new team member rather than a drop-in replacement for a seasoned expert with years of specific system knowledge.
That could be a good way to frame his current capabilities based on this finding. And, even with all these checks, the messiness analysis, SWE-bench, the internal PRs, the researchers are careful to point out limitations. Their task suite, even with its diversity, is still systematically different from the full complexity of real-world jobs. The tasks are mostly automatically scorable, which limits open-endedness. They don't involve interacting with other people or agents. Resource constraints like time or compute are often pretty lax in the tests. Mistakes are usually not very punishing. The environments are mostly static, not constantly changing.
Right. All those simplifications mean the rapid progress they measured might not perfectly one-to-one translate to all aspects of complex, real-world intellectual work.
Exactly. There's still a potential gap between this measured progress and its full, real-world economic impact. The generalization isn't guaranteed to be perfect.
Okay, understood. Nuance is key. But even with those caveats, the underlying trend seems robust and frankly pretty dramatic. So if we do take this observed trend seriously, what does it forecast for the future? Where does this exponential curve lead?
This is where the paper gets bold. They decided to extrapolate the trend. If, and it's an important if this observed doubling trend continues and it generalizes reasonably well to real-world tasks, they project that AI systems capable of automating many tasks that currently take skilled humans about a month could arrive somewhere between late 2028 and early 2031.
A month. We're talking, 160 plus hours of focused human work?
Yeah, over 167 work hours is the mark they use. And this forecast is for AI reaching a 50% success rate on tasks of that duration.
Late 2028 to early 2031. That's really not that far away. Why pick 1 month as the threshold to forecast? Why is that time frame significant?
They argue it's significant because it's roughly the timescale where a new human hire often starts generating net positive economic value for a company.
Ah, okay, the point where someone is contributing more than they cost to onboard and train, roughly.
Exactly. So, reaching that level of capability, even at 50% reliability for month-long tasks, would likely be considered truly transformative AI by many economic measures. It's a threshold for substantial, sustained value generation.
Gotcha. So what could speed this up even more or potentially slow it down? Are there known factors that could bend that curve?
They discuss a few key possibilities. On the acceleration side, advances in agency training, specifically training models not just to predict text, but to be better sequential decision makers, better agents that could potentially steepen the curve.
Makes sense. Better planning, better strategy.
Right. On the potential flow-down side, there's compute scaling. Training these massive models requires enormous amounts of computation, which has been growing exponentially. They mentioned a 10,000x increase since GPT-2.
Wow.
But there might be physical or economic limits to how long that exponential growth can continue, although they note that algorithmic improvements, finding smarter ways to train, have often compensated for compute limitations in the past.
So maybe we get smarter even if we can't just keep throwing more chips at it indefinitely.
Possibly. And then there's the really big potential accelerator, the automation of AI R&D itself.
AI helping build better AI, the recursive loop.
Exactly. If AI systems become capable enough to genuinely assist or even partially substitute for human AI researchers and engineers, that could create a powerful positive feedback loop. Progress could accelerate dramatically.
That feels like a potential phase shift. But just measuring these capabilities must get harder as they improved, right? How do you even create and evaluate tasks that take a human months?
It's a huge challenge. They acknowledge that accurately measuring these very long time horizons requires enormous data sets of genuinely difficult, long tasks. Creating those is impractical, and evaluating success often requires slow, expensive manual grading, not automatic scoring,
Right.
and measuring very high success rates like 95% or 99% reliability on complex, long tasks. That's even harder. You need so many trials to be statistically confident.
So our ability to precisely track the frontier might get fuzzier as the frontier advances to these very long timescales.
It likely will, yes. Measurement itself becomes a bottleneck.
And just to throw out the ultimate possibility, what about artificial general intelligence, AGI? If we ever reach that point, what happens to this time horizon metric?
Well, if you define AGI as a system capable of completing basically all tasks that expert humans can, and doing so with high reliability, its time horizon would effectively become infinite, right? It could tackle tasks of any duration.
I see.
In that scenario, the trend wouldn't just be exponential. It might look even faster as it approaches that asymptote. The rate of capability gain could potentially increase as it nears full human-level generality. But that's obviously highly speculative territory.
Understood. So let's just recap the core insight from this MBTR study for everyone listening.
The main takeaway is that AI capabilities, when measured by this new, more intuitive time horizon metric, how long a task takes a human expert versus AI success rate, seem to be increasing at a remarkably consistent exponential rate.
Doubling roughly every 7 months based on the data since 2019.
That's the number. And this progress appears driven by concrete improvements in the AI's reliability, its ability to reason logically, and its effectiveness in using tools, not just scale alone.
And while we absolutely need to keep the caveats in mind, the difference between these benchmarks and the full messiness of all real-world work, the underlying trend itself seems undeniable.
It really does. And it presents some pretty profound implications for, well, the future of work, how we structure research, maybe society as a whole. The potential for human-AI collaboration is changing rapidly.
Absolutely. This deep dive into MBTIR's research certainly puts that rapid change into a much clearer, more quantifiable perspective, gives us a new lens to watch this space. So maybe a final thought for you, the listener, to chew on.
Yeah.
If an AI could genuinely perform tasks that currently take a skilled human expert a whole month, even if only with 50% reliability initially, what kind of entirely new problems, new challenges, maybe new scientific frontiers would you suddenly be able to tackle if you had access to such a powerful assistant? What could human ingenuity achieve when boosted like that?